Notes 8.3, comparing functions. So it says three trains, A, B, and C. Okay? We have train A in a graph, train B's equation, and train C we have as a table. And they leave the station at the same time. The graph shows the relationship between the time and distance for train A. Okay, so we've got time on the x-axis, distance in miles on the y-axis. Same thing here, time in hours, distance in miles. So I'm sure train B is going to be the same thing. We're talking about miles per hour. So it says, what is the slope of graph A? So when I think slope, I want to think about my rise over run. So I would absolutely pick two nice points, and that looks like a good one, and that one right there. And how much am I rising up and how much am I running? So my rise is 120 miles divided by my run, which is 4 hours, okay, which then gives me 30 miles per hour for that train. So 30 mph is my slope, okay, or my rate of change. So what's my slope in train B? Okay, we've got the equation, and we know my rate of change is 45 miles per hour. And it says, what does the slope represent? Okay, so we know that the slope represents miles per hour. Okay? And in that case, the train A, is moving at 30 miles per hour. And it says the relationship between time and distance for train B, okay, so train B, I should change colors here. Train B, that we have our equation for, is given by the equation above, where x represents hours, that we already talked about that, and y represents miles. Find the slope m. Oh, I answered that already. We said it was 45 miles per hour, because when we have an equation, okay, we think about y equals mx plus b, where m is our slope, so 45 miles per hour for train B. So it says, which train is moving faster, train A or train B? How do you know? So we know that train B is moving faster because the slope, okay, or the rate of change, okay, is, let's see, train B is moving faster because the slope is larger. Okay, train B, we said, was moving 45 miles per hour. That's certainly faster than train A, which was 30 miles per hour. Now it says, where am I? Okay, here we are. The time-distance relationship for train C is shown in the table. All right, so train C, we're going to look at on the table. What is the ratio of distance to time? So in other words, ratio of distance to time, they're asking for the slope, or they're asking for the rate of change. All of those mean the same thing. So let's go back up and let's figure that out. So we've got, what is this going up by? We're adding 3 each time. Now those are my x's, or my inputs. And then what's happening, okay, with that, we are adding 105, it looks like. Yeah. And again, we're adding 105. And from 315 to 420, again, you're adding 105. So what is my rate of change for this? Remember, we have to have our change in our y over the change in the x. So that's 105 divided by 3, which gives us 35 miles per hour. Because remember, this is miles and this is hours. So down here, probably could take it, I probably could move that. See if I can grab this. Nope, that'll move too much. All right, so let's write that down here. So my, whoops, so my slope is, we'll just rewrite it, 105 miles divided by 3 hours, which is 35 miles per hour. Okay, so that's train C. Compare the speed of train C to the speeds of train A and train B. So let's make a nice little list here to organize our thoughts. Train A, train B, train C. Okay. So train A we came up with, and that was moving at 30 miles per hour. Train B is moving at 45 miles per hour. And then we just found that train C is 35 miles per hour. So which one's the fastest? Okay. That one's the fastest. Train A is the slowest. Okay, and train C is the medium speed, right in the middle. Okay. All right, so let's go ahead and flip the page. Okay. So example 2 says that water is pumped into 2 aquariums, P and Q. So we have aquarium P and aquarium Q. The tables show 2 functions relating the total amount of water, Y. So here's my Y, which is my total, and then my time is T minutes. To pump the water into each aquarium. Okay, so we've got these 2 aquariums, water's being pumped into them, and let's see what kind of information we can come up with. It says write an algebraic equation to represent each function. Okay, to represent each function. So we've got aquarium P, we're going to have to do some work on, and then aquarium Q. So let's split it up. So we've got to write an algebraic equation for both. So it says, let's find some patterns here. So we can find our rate of change. Now it's going to be plus 5, then we have plus 10, plus 10, and then we have plus 50, plus 100, plus 100. So now let's do some comparing. Okay. My change in my Y over my change in my X. So that one, that first one, 50 divided by 5 is 10. Okay, 10 liters per minute. Let's see what we get with this one. We get 100 divided by 10, which is 10 liters per minute. So far, it's a constant. And let's see, that last one, 100 divided by 10, again, gives me 10 liters per minute. Okay, so we know the slope, okay, for aquarium P. So we know it's linear, so we know it's y equals mx plus b. So right now, we just found the slope, but we don't know the y-intercept. We don't know how much it started with. Okay, so we got to do some figuring there to find out the b. Okay, so what we can do is we can take one of our points. I don't know, let's start with the smallest one. Let's start with 570. Okay. And let's use that information. So if I say 70 is my y, 10 was my slope, the x for my 570 is 5, plus the b, because that's what we're looking for. So 70 equals 50 plus b. Now, if I want to get BL by itself, because that's what I'm looking for the y-intercept, the starting point. How much water was in this aquarium when we started? So it's 20. So I can go back and take out that blank there, and I can put in what we just found, 20. So that's going to be for aquarium P. Okay, now let's do the same thing for aquarium Q. So let's see, is it linear? So we still do, that's plus 5, plus 10, plus 10. The times are the same. Okay, and now let's figure out from here to here, that's going to be a plus 75, and then that's a plus 150, and then that one's also 150. So again, let's do some of that division to find our slope to see what our rate of change is. So the first one, 75 divided by 5 gives us 15 liters per minute. And then the second one, 150 divided by 10, that's 15 liters per minute. And do the same thing, yep, that last one, again, 150 divided by 10, 15 liters per minute. So we know that it's linear, and we know our rate of change, or our slope, for aquarium Q. So we know it's linear, so we can start off with y equals mx plus b. Y equals 15x plus b. I have to find the starting point. How much water does this aquarium start with? So let's go back to our table. I'm going to pick that point, that first point there, just because it might be easy to work with. And I say, okay, my y is 95 equals 15 times 5 plus b. 95 equals 75 plus b. Now I've got to solve for b. So I'm going to subtract 75 from both sides. And b is 20. So I can go back into my equation and take out that b and put in what it started with. It started with 20. So that's for aquarium Q. So let's see what kind of information they're asking us. It says, which of the two aquariums is filled with more water quickly? Okay, so more water quickly. So what we've got to look at is we've got to look at our rate of change. 15 for aquarium Q and 10 for aquarium P. Which one is going to be filled faster? Okay, Q is filled faster because it has a larger rate of change. Okay, it's being filled at 15 liters per minute, and aquarium P is only 10 liters per minute. Okay, and then which of the two aquariums started with more water? So the starting point, the y-intercept, the starting point, the y-intercept. So look at this. Starting point for Q is 20, and the starting point for P is 20. So they're equal. Okay, they both started with 20 gallons. They both started with 20, I think it's liters, yeah, liters. Okay, so they're the same. All right, so again, we're going to come back to class and do some more practice with our rate of change with our linear function.